These are my favorite memes of the week. I thought Yoda is always good. I don't know if anyone else experiences this, but it's like whenever you wake up in the middle of the night, it's really hard to go back to sleep, especially if you have to go to the bathroom. Anyways, Carolina, I know you've seen this one before, but it's really funny to me. Ha, ha, ha. Succulent jokes. Then I had this guy in here because they got you in the first half. All right. And then my last one is more of a dad joke. Ha. That's hilarious. Anyways. Also, I think it's funny because soup is usually heated up and Elsa freezes things. Anyways. Hopefully those made you laugh because today we're going to talk about t-tests. And I actually think coming from last week, t-tests are going to be a little bit easier than regressions. So I'm hoping that's the case for you guys. But this is kind of where we get into comparing means. So last week we talked about when you have both parametric dependent and independent variables, right? So you're working with all measured data. And we use correlations to form relationships, right? Or to see if relationships are significant or not. We use regressions to see if we can use existing relationships to create predictive equations, right, for certain dependent variable outcomes. Okay, so this week we're talking about t-tests. If we go back to our flowchart that I kind of gave you guys a couple weeks ago, right, we kind of checked off regression and correlation. So this week, if you follow the yellow brick road, right, that's the pathway we're working with in our decision tree. So still working with a parametric dependent variable, right, something that has been quantitatively measured, which again, all of our examples are going to be ratio data in this class. When we look at our independent variable, however, instead of parametric like we used in regression and correlation, we're going to have a non-parametric independent variable. So this will be nominal in all of the examples for our class, or categorical, right? So some type of independent variable that's going to have different categories or different groupings in which all of the subjects in a group share a common characteristic. Right, so for the activity last week, I gave you guys some feedback because we had a nominal independent variable with the Huntington's disease research question, right, in which case we had a non-parametric independent variable that had two levels, one being a control group or having no treatment, the second, or no intervention, the second group would be our experimental group that does have a treatment. So oftentimes when we work in a t-test, we're only going to have one independent variable that's non-parametric, and it's only going to have two values or two classifications, two categories, two groupings, whatever sticks with you, okay? Within these two groups, we previously talked about between and within subject designs, okay? Does anybody remember what a between subject design would indicate about the subjects being used? Anyone? Takers? Guesses? Possibly type in the chat if you want to. There's a hint in the box. You have a 50% chance of being right.
What was the question again?
So what does the between subject design indicate about the subjects being used, or how you might group people into these two different categories of your independent variable.
Split between subjects.
Right, so between subjects splits the subjects. Okay, so we have these two groupings, right, based on whatever our non-parametric independent variable is measuring. Okay, if we use different subjects in each of those groups, we would have an independent t-test that we would be running, right? So we would say mean of group A versus mean of group B, and then we compare them together, right? That's basically what a t-test does. If we use the same subject, so in the case of the activity last week, right, where if we took any one of those different balance outcomes based off of either intervention or no intervention, right, the actual independent variable is just looking at time of measurement, right? So it's like a pre-test, post-test situation where we're saying, does the intervention actually make a difference in a given balance outcome, right? So in this case, or in that example, that was a within subject design, which most of you got correct, right? Because we would be using the same subjects to measure the pre-test measurements as well as the post-test measurements, okay? In other words, they fall into both groupings of the independent variable. So we would use a paired t-test to do something like that, okay? There's another type of t-test that we'll talk about. It doesn't really fit into the flowchart well. That's why I exclude it. And we're also not going to focus on it too much in terms of as far as like it being on an exam per se. So independent and paired t-tests are going to be the ones that you want to focus on for this exam as far as procedures go in SPSS. Okay. All right. So why run the t-test? I kind of alluded to this already, right? But if you want to know the effect, right? So now we're talking about effects. I made that comment on some of your activities last week, right? Or maybe 2 weeks ago. I think it was activity 4. Okay. So when you want to know the effect on something, right? Or the effect of a manipulation of an independent variable and how that changes any dependent variable measurements is basically when we run a t-test, right? We're comparing means between two groups. And there's a couple of different ways that we can compare these means. One, we can look at the odds that a sample has been collected from a specific population, right? So that's kind of the statistical inference concept, right? Where we have to say, does a sample, is it representative of the population or is it significantly different from the population, right? And we do this largely based off of estimation most of the time. This week, we'll have estimated population parameters. I'll go into more of that once we get into that type of t-test. But, right, we can see how representative is a sample of a specific population by comparing different means. We can also have two samples, as in an independent or a paired t-test, where we try to see, are the means of those groups, based on whatever we're measuring, right, are they similar enough such that we could say they've been measured from the same population? Or are those means significantly different such that we could say they've been collected from different populations or they're representative of different populations? Okay. Because remember, the whole concept of statistics is to be able to infer your calculations or your results to a larger group of people. Okay. So, with that being said, remember that odds represent a probability, right? And in our case, probabilities represent p-values. So basically what we're looking at in the statistics, right, is does the p-value come out significant in terms of distinguishing group means, right? So is group A significantly different from group B? is pretty much the base idea of how t-tests are going to operate. We do have generally this equation here, okay? And this is to calculate a t-ratio or t-statistic. We can also call these t-scores. We introduced these last week when we talked about finding t-statistics for the B coefficients that you guys use to make the regression equations, okay? So it is important to note two things, okay? The t that we calculate this week is going to be different than the t we calculated for the B coefficient. We evaluate those t-statistics the same way using the t-table, but in terms of calculations, they mean different things. So the t-statistic for a B coefficient was testing how good is the relationship such that that value is going to be a predictive factor for an independent or for a dependent variable measurement, right? So you have to look at the context of what you're actually measuring t for in order for you to see what the actual value of t is referring to, okay? So this week we're using t to look at mean differences, right? So I mentioned you're looking at a difference between a group, the mean of group A versus the mean of group B, right? So you're going to be given two means, whether that's from a sample and an estimated population mean, or if it's from two different samples, right? Either way, you have two sample means. You want to see what is the difference between those. And if we put that difference into a population, right, we have the standard error of the mean difference, or standard error of the difference, as we'll refer to that, right? This is, remember, standard error tells us how far away certain sample statistics are from what we would assume would exist in the population, right? So incorporating the standard error part is what gives us our statistical inference abilities. And these are, the standard errors are going to be calculated in various ways based on the type of t-test we're running. But generally, if you just have one sample and an estimated population versus two samples, which could be between or within subjects, these are the general equations on how you would calculate your t-statistics, okay? So again, t-statistics or t-ratios are telling us in terms of a t-test, right, how big the mean difference is between two groups, basically. Okay, so that brings us to the different types of t-tests, and this is the order that we will go in for our lecture today. Okay, so single sample t-test is going to be similar to the first equation on the last slide, where we're looking at a sample versus an estimated population mean. And then we have our independent t-tests and our paired samples t-tests. These are also often referred to as dependent t-tests, which kind of makes sense because of the way that the samples are used within the test, right? Independent, meaning that the samples are independent or separated from each other. Paired samples, meaning that you have the same person being paired, okay, as far as measurements are concerned, okay? So before we get into the nitty-gritty of each of these tests, all t-tests have to adhere to certain assumptions, okay? Every single one of them is going to have a normally distributed population from which a sample is drawn, right? Which also means that the sample needs to be normally distributed, right? So just think normal distribution. And then our samples also have to be randomly selected, okay? So anytime you see assumptions on a test, the first two things you should write down are normal distribution or normally distributed data and random sampling, okay? The next assumption that we're going to have comes from our decision tree, and that tells us what types of variables we're working with, right? So we know we're going to have one parametric dependent variable, and one non-parametric independent variable that specifically only has 2 categories or 2 levels. And then lastly, if we're working with an independent or paired samples t-test, we have to check to look at we have to check the variability of the samples, okay? And this is only if you have 2 samples. So this variability assumption does not apply to a single sample t-test, okay? But if we have a between subject design or an independent t-test, we use this test called it's called homogeneity of variance, okay? And we use a test called Levene's test. To go through this, I talk about Levene's test a little bit more in the activity video because it actually is shown. But this test is going to come up for the rest of the semester. So understand what homogeneity of variance is. Know that it is it's an assumption. I go into more of this when we get to the actual discussion of homogeneity of variance. So just for reminders, you really need to know what this test does, okay? For within subjects, we can also check for homogeneity of variance, but we do it in a slightly different way because instead of comparing sample variances, we're basically saying, does data set A correlate to data set B? Because basically what we're doing in these variabilities is we have to say, are the subjects similar enough that we can actually statistically compare them, okay? So I go into both of these a little bit more, and hopefully that makes sense a little later. But these are the primary assumptions that we're going to have to meet for t-tests, okay? The other thing, yeah, go ahead, Oscar.
By 2 levels, do you mean like control group and experimental, or?
Right. Mm-hmm.
All right.
Yeah,
All right,
and
thanks.
sometimes you can have 2 experimental groups. It kind of just depends on the layout of the study. But generally, what we'll see is a control versus experimental. And I have some examples later, so hopefully that'll help clear it up too. But we also have degrees of freedom. So last week, when we looked at the t-table, we calculated degrees of freedom by taking the sample size minus however many variables we were working with, right? This week, degrees of freedom are going to be calculated based on the number of samples, okay? So if we're using a single sample t-test, obviously we have a single sample. So degrees of freedom is going to be n minus 1 for 1 sample. If we have an independent t-test, we have 2 independent samples or 2 separate sets of people. So we take the total sample size of the 2 groups combined and subtract by 2, which is representing the 2 samples that we've collected, okay? For a paired samples t-test, we have 1 repeated sample, right? Or 1 sample that's being used twice. So we only take a degrees of freedom for that single sample, right? Even though we use them twice, it would be redundant to put 2 degrees of freedom. So we only put 1, right? So generally, when I have you guys study this information, that's why last week I said it's n minus the number of variables. This week it's n minus the number of samples. So if you understand how to calculate degrees of freedom for certain statistical tests, once you evaluate, okay, well, how many variables do I have or how many samples do I have, it's kind of more intuitive to figure out what your subtraction factor is. Okay, so this will be important for you guys when you read the t-table later, because the way that you read it is the same. If you remember, in the t-table, the first column is degrees of freedom, right? And then the rest of the columns are representative of different levels of confidence and the critical values that exist at those levels of confidence and degrees of freedom. Okay, so this will come in handy when you actually read the table for your activity as well as the practice problems that I put in the lecture. All right, so we'll go into more of the complex stuff within each test. For a single sample t-test, again, we're only looking at a single sample, right? And we're comparing the mean of that single sample to estimated population parameters, okay? So in order to calculate, or in order to distinguish this t-test from other t-tests, you are going to be given one sample, and you likely will be given an estimated population mean in the actual question, okay? Basically, the purpose of this test is to determine, right, if whatever your sample is significantly different from the population, okay? And basically, that means you're kind of determining, does the sample represent the population? Was it drawn from that population, or was it maybe drawn from a different population, right? If you have a significant difference, you likely have a sample that is, or the sample kind of is inferred upon a population other than what you thought you originally took up, okay? So if we look at the t-ratio calculation, right, remember we look at actual mean difference, which is going to be the difference between the sample mean and the estimated population mean, and that'll be divided by what we would expect the mean difference to be in the population. So remember, whenever we look at what would we expect, or how would we infer this information on a population, we always use standard error. So the standard error of the mean, this was given to you guys 2 weeks ago, I believe, when we were calculating the confidence intervals for a true population mean. I do want to clarify, because this might seem similar to that calculation. So if you guys recall, you did the sample mean plus or minus z times the standard error of the mean, okay? You would only use that equation when the population mean is trying to be estimated, or you want to find where the true population mean would lie, given a sample, given a sample statistic or a sample mean. This one, you have an estimated population mean. That mean isn't actually known, right? That's why we say it's estimated, but you have an estimated population mean that you're working with, versus the z-score one. The population mean is technically already known, okay? So t-ratios are a lot more common than use of the z-score confidence interval equation, just because we don't usually actually know the population mean, okay? But you would take what the actual difference is, right, that exists within your sample, and then you divide it by the standard error of the mean, which is just standard deviation divided by the square root of n, okay? From here, right, this gives us t, and then we can use whatever our degrees of freedom are at a given level of confidence. Remember, we usually have that information prior to going into our test, okay? And then we can locate what critical value exists on the table at that given degrees of freedom and level of confidence. And then we compare the calculated t, right, from this equation up here. We say, is that t statistic large enough to be significant, okay? Because the critical value is going to say, this is the actual measured difference that we would need in order to be significant at a given level of confidence, right? And that number is going to change as you increase your sample size, also as you fluctuate your level of confidence. But the critical value tells you this is how big the difference actually has to be. So if your mean difference that is calculated, right, ends up being larger than the critical value, that means we have a significant difference between the means, okay? We can also calculate a confidence interval. It should look very similar to the confidence interval that you guys have used, but instead of a z-score here, we have the critical value t, okay? So this critical value here represents the t-score that is at your degrees of freedom and given level of confidence. Okay, I think it's really easy to confuse this t-score critical value with the calculated t. They are two different things, okay? And you should have gotten some practice working with this nomenclature last week in the practice problems for regressions when you were looking at critical values for the B coefficient for bivariate regressions, at least, because that was the example that we used them for, okay? All right. Are there any questions on the equations or generally how to read them? Cool. All right. So with this, each test has a null hypothesis, okay? The null hypothesis for t-tests, similar to a lot of other tests, can be worded a lot of different ways. So I like to give you guys options. That way you pick the wording that works and makes the most sense to you. And then you just keep that wording for the rest of the semester, pretty much, okay? So when we're looking at the null hypothesis for the main effect of the test, the main effect is representing the differences between the means, right? If you remember, or if you look at the t ratio that we calculate, it's always going to be looking at the mean difference, right? So that's the main effect that we're investigating. We could say the null hypothesis, right, directly translates to there is or there is not a significant effect, right? So the null hypothesis would always say whatever the independent variable is, it has no significant effect on dependent variable outcomes, right? You could put it in terms of the difference between the means, right? So we could say the difference between the means of the treatment group and the population, in this case, because those are the means that we're comparing, right? Those are not significantly different. We could also infer this to, is the sample representative of the population that we were originally comparing it to? So null hypothesis would say the treatment group or the sample is not significantly different from the population in terms of the dependent variable outcomes. Thus, we could say that the sample, right, is representative of the population, or it is drawn from the same control population, right? Based on your p-value, or the p-values that you get for this main effect, right, that'll determine if you reject or accept these null hypotheses. Again, pick one. I personally like the first one the best because it's the easiest. As long as you know what the independent variable is and the dependent variable, you're pretty much good to go. It's a plug and chug type of wording to use. But remember, in this case, t-tests are going to be looking at cause and effect. Okay, so you would actually use the word effect, versus correlations and regressions are going to be looking at relationships and predictive relationships, respectively. Okay. So these are different null hypotheses that you could use for a single sample t-test. Let's go through an example. So let's say we're looking at the effect of a 12-week training program on ankle sprain injury rates, right, in volleyball players. What would my independent variable be in this question or this setup?
Training program.
Training program. How many levels would we say that has?
2.
2. Reasonably 2, right? We could say you either don't have people who go through a training program or you do, right? What would the dependent variable be?
Ankle sprain injury rate.
Yep. We're looking at injury rate. Okay. So independent variable is identified as a training program. In this case, since we have a single sample t-test, we're going to have an experimental sample. So that'll be the sample mean that goes into our equation, right? And then we're going to have a control group, which is basically representative of the estimated population mean, right? So maybe we have nationwide ankle sprain injury rates from a whole bunch of volleyball players, right, over whatever age group that we're investigating. Okay, and that is our estimated population mean. So we're just trying to see from a representative sample of this volleyball player population, if we manipulate these people in a certain way, is there a significant difference, right? So again, dependent variable is ankle sprain injury rate. And our hypotheses, again, we always are going to use two-tailed tests for this class. So we're basically just trying to see, is there a significant difference? We're not saying that they're going to improve their injury rates, or we're not going to say they're going to increase or decrease their injury rates. We're just saying there is going to be a difference, right? So null hypothesis would argue that there is no difference between the means, right? In other words, the difference would be 0. The research hypothesis is mutually exclusive to that statement and says there is going to be a difference, right? Again, not indicating direction. Does that make sense? Participant response buttons. Very good. Yes, cool. All right. So I've given you guys some, oh, there might be a question in the chat. Oh, yes, cool. All right. These are some practice problems. In the lecture section on Beachboard, I put a, a spreadsheet in there that kind of has this information organized in a certain way that you just put the numbers in and then can calculate. So I would watch that video if the calculations don't really make sense. Also watch the video because I go more in depth on how to read the t-table based on the calculations that you run. Okay, so I'm going to skip over this slide, but please do try the calculations. All right, so that's our single sample t-test. We now have our independent t-test. Okay, remember independent is referring to independent samples where we have a between subject design, right, where different people are going to be in each of our samples. Okay, so we're basically trying to say, are the mean differences between these samples significantly different from each other, or are they similar enough that we can say they were drawn from the same population? Okay, too far, go back. All right, so as far as the t-ratio is concerned, right, it's still measuring the actual mean difference between the samples and then comparing that to what we would expect the mean difference to be if we compared it to a population. Okay, so again, the top part, you're just taking whatever the two means that you've been given, what is the difference between them? Okay. One thing I do want to note, and I highlight this in the activity as well as the practice problem video, is that you're going to be looking at the absolute difference. Because the way that we can organize these means when we put them through SPSS, we define the order. So if we say I want variable 1 to go first and followed by variable 2, the difference that we get is either going to be positive or negative. That positive or negative doesn't necessarily matter in terms of our calculations when we compare our calculated t-statistic to our critical values. What you're really interested in is the absolute difference, okay? So if you take the absolute value of the difference, right, that would always give you a positive number and tells you what the total deviation between those two means is. What the sign would indicate, if you have a positive difference, that would mean variable 1 is larger than variable 2. If you have a negative difference, that means variable 2 or sample mean 2 is larger than sample mean 1. Right? So it doesn't necessarily mean that your t-statistic is greater than or less than. It just tells you the direction of the deviation. Okay. As far as the standard error portion, we're looking at the standard error of the difference between the means. So in a single sample t-test, we use the standard error of the mean. In a independent t-test, when we have two samples, we basically are just looking at the square root of the standard error of the mean. Okay, so the reason why we put this in a square root and then you can see standard deviations are squared, it's basically the same as saying standard deviation divided by the square root of n, right? If you kind of split it up, go back to your algebra days, okay? So we can write it a couple of different ways, and based on how I present information to you guys, you'll know which version to use. Both of these will be provided for you on the exam, so it doesn't really matter as long as you understand order of operations and how to insert your equations into your calculator or into Excel, okay? But the concept is generally the same, right? We calculate this t-statistic, which is representing our mean difference, and we have to evaluate, is that mean difference large enough to be significant, okay? Or to say that our groups are significantly different from each other. So again, our degrees of freedom is going to consider the sum of our samples put together, not divided by, minus 2, which is representing how many samples we've collected, right? So if you took the degrees of freedom for each sample, that's why I wrote it this way as well, right? It comes out basically to this total sum of your sample size minus 2. Okay, but at your given degrees of freedom for your example, and at the given level of confidence, you can have a critical value, right? And then you just compare, is the mean difference between the samples significant or big enough to be significant, where we would have a p less than an alpha, okay? Similarly to our last example, right, for a single sample t-test, we can calculate confidence intervals for an independent t-test. Basically, the confidence interval tells us the true mean difference, right, between two given populations, one that has a treatment, one that does not. The difference would be this number, okay? So it's not uncommon when you're calculating confidence intervals for t-tests to see negative numbers, right, because you can either have a negative difference or a positive difference, okay? But basically, what you're looking at is the difference between the means, plus or minus, again, the critical value in the t-table, so critical value, times whatever your standard error measurement was. In this case, it was the standard error of the difference, okay? Sure. Similar, again, to our single sample t-test, we have different null hypotheses. There's a couple of different separations that I need to make, though, because if you recall from our assumptions list, we had normally distributed data, random sampling, our independent and dependent variable characteristics, as well as our homogeneity of variance assumption, okay? Homogeneity of variance, and I'll say this twice if you want to write it down, okay? Homogeneity of variance is looking at the equality of variances between samples, okay? I might actually, you know what, I can put that in the chat.
One more time.
Yeah, I'm gonna type it in the chat box so you guys have it there. Okay, homogeneity of variance is looking at quality of variance. Okay, so it's the equality of variance between samples. So you guys can copy that and put it in your notes if you need to. But this assumption, it can't be assumed without calculation, okay? So homogeneity of variance is going to show up in your SPSS output, and then based on the results of that test, you'll understand how to further read your t-test results. And that'll make more sense when I go through the process in the activity video. But if you get if you get a p-value for any test in SPSS, that means that there is some null hypothesis that goes along with that p-value, okay? So this homogeneity of variance assumption is tested in SPSS, and you get a p-value for it, okay? Basically, it's saying that there's equal variances between groups. So there's, again, several ways that you could say this. You could say the variance in group 1 is relatively equal to the variance in group 2. Or we could say equal variances are assumed. That would be another way, right? But basically, when we run this test, right, what do you guys think the p-value should be? Less than 0.05 or greater than 0.05? What do you think we might want? To accept this or to reject this?
Less than.
Less than meaning we would reject this?
Yeah, because it's significantly different.
Uh-huh. Do we always need to prove significance? I'm kind of glad that you answered that in that way.
For this test, because t-test, if it is significantly similar, then yeah, we won't be doing that. Right.
What would be significantly similar?
That's a tough question to answer.
No, this is good though. I'm glad you're phrasing the question this way, because this is a part of t-tests and ANOVAs that are very commonly misconstrued, right? Because you have a p-value for your main effect of your test, but you also have a p-value for the assumption test. So if this is the assumption test and we can't accept the results of our t-test without meeting these assumptions, that would mean that we need this null hypothesis to be true. In other words, we would want the p-value to be greater than 0.05, okay? So this was a very good conversation to get to this point, okay? We always want the null hypotheses to be true for assumptions. Therefore, we're always trying to look for a p-value greater than 0.05 for assumption tests. In this case, our assumption test is the homogeneity of variance, okay?
So we are trying to have it true, whatever we possibly can do to make it true.
Right.
If it is not true, then.
Yeah. If it's not true, then we have to apply correction factors, which are okay, but sometimes can interfere with the validity of the test. So an example being, you guys know variance is a measure of variability, similar to standard deviation, okay? So whenever we have a larger sample size, generally we should see that standard deviation or variance decreases, right? Because we have a more representative sample that's tighter into the center of a normal distribution, okay? So in the case where we might have, like say we have a sample of 20 versus a sample of 40, that would probably render a situation where we would need to apply a correction factor because our samples wouldn't be similar enough, or the variability within their distribution isn't similar enough to compare them statistically, okay? So homogeneity of variance just, whoa, that was weird with the mouse. Homogeneity of variance is just saying the variability within our samples needs to be relatively the same so that we can actually compare them in our test, right? So we're looking for, when you look at homogeneity of variance or the Levene's test in your output, you want the null hypothesis to be true, or you want the p-value to be greater than 0.05. If it's not, it's okay, because SPSS will give you two different readings, right? So the correction factors are automatically built into the outputs. You just have to know when to read them versus when to not read them. And that's where it gets confusing. But that's also why I gave you guys flowcharts. Hopefully those help. All right. So p-value greater than 0.05 is desired, right? And then, as I said, if not, we have a correction factor that's applied by the software. Okay. So this is, again, for the assumption. When we look at the null hypothesis for the main effect, this is where we're relating our independent and dependent variables again. So basically, these different variations are going to be exactly the same as a single sample t-test. The only difference is now we're comparing two samples that we've collected instead of a sample and a population mean. Okay, but we're basically looking at, is there an effect of the independent variable on the dependent variable, or is there a significant difference between the means for the two groups measured? Okay, so we can look at this, a same example, right? But maybe instead of the way we organized it last time, we say independent t-test, right? So we already said our independent variable is the 12-week training program, and our dependent variable is our ankle sprain injury. If we're using a t-test, that means we've got two levels of this training program. Okay, so in an independent t-test, we're using different people in each sample, right? So therefore, this is a good example where we'd have a control sample and an experimental sample, right? Maybe we have equal sample sizes, right? So 20 and 20. Some people don't receive the training program, some people do, right? With those samples, we take ankle sprain injury rates and we generate hypotheses based on what we think will happen, right? Again, if we're using a two-tailed test, we just want to see, does the training program have an effect on ankle sprain injury rates? We don't care if rates increase or rates decrease. We just want to know, are the means relatively equal to each other, as the null hypothesis would argue, or are they significantly different from each other, which is what your research hypothesis would argue. Okay. Any questions on independent t-tests?
So it is basically like a correlation factor kind of thing, like we are relating it if it is there. Is it making sense?
I think the idea that you're drawing from is correct, but you just want to make sure you say effect, not relationship, because correlations are going to be different from t-tests in that respect, where, remember, we said correlations don't prove causation, right?
Mm-hmm.
So correlations, we're just saying two variables, are they related, or do they have a pattern of relation such that, and then if you draw it into the regression side, are those relationships strong enough to be able to predict the outcomes of a given variable, right? Those are going to be different from t-tests, where we're saying, does a certain intervention or does a certain treatment, is that going to cause an effect, right, in a dependent variable outcome?
Okay.
Does that help distinguish the two?
Yeah.
Awesome. Anybody else on independent t-tests? It could be on previous slides for this chunk, or based on this example. Good. All right. So here are practice problems. I put in equations for you guys. There's a couple of examples. There is, I will say, just to give you guys a heads up, there is a question that has to do with calculations on the quiz. So I would recommend attempting the practice problems before you use an attempt on the quiz, just so you don't waste it, okay? But you'll have to calculate or see if the conditions are significant, right, with the p-value greater than or less than 0.05, right? And then you're also going to calculate the confidence intervals that would represent where the true mean difference would be located. Okay. red. So then we go into paired sample t-tests. So this is practically identical to independent t-tests as far as general concepts go. The only difference is that we have the same subjects being measured in each group or each sample that we've drawn, right? But the general conclusions, right, are these samples drawn from the same population or are they drawn from a different one, are going to be the same, okay? The actual calculation concept is exactly the same as an independent t-test, right, where we're looking at what the actual difference is between the means divided by the standard error of the difference. So on an exam, for both independent and paired sample t-tests, you will get this one equation for a t-statistic, okay? However, the way that we calculate the standard error of difference is not the same as an independent t-test. And that's because we have to put in this correction factor, right, that we build in that is relative to R. And we'll talk about that in the next slide. But pretty much once you calculate the standard error of difference, right, that goes in the denominator of your t-ratio formula. That tells you how large your actual sample difference is, right, compared to a population. And then we say, is that difference big enough or larger than the critical value to be significant, okay? As far as reading the t-table goes, all the same process, right? Just remember degrees of freedom is n-1 because you have only one sample that you've collected. Even though you're repeating the use of that sample, it's only one sample. Right? Confidence interval is calculated the same way as an independent t-test, so yay for repetition on formulas. Okay. I do want to talk about R, though. If you guys remember, R is a correlation coefficient. Okay. So this is kind of like our homogeneity of variance concept for paired samples. We don't label it necessarily as homogeneity of variance, but it's comparable, right? Basically saying that if I was measured for a dependent variable, let's say we're looking at, I don't know, let's say we're looking at the effects of stretching on flexibility, okay? And I'm part of both groups where we're looking at prior to the stretching program and after the stretching program, okay? So I'm going to be measured for the baseline test or the pre-test, and then after we do the stretching program, I'm going to be measured again for the post-test. We have to say that those two measurements are similar enough that it can be included that I was the sole person who was measured for both of those values. Okay, so that's why we take this correlation coefficient, because generally, right, if like I'm a very flexible person, so my outcomes are going, they should be relevant to my starting flexibility, right? It's not like I'm going to get drastically less flexible or drastically more flexible, right? It all obviously depends on the stretching program, but generally people who have a lower degree of flexibility to start would also be predicted to have a generally lower measurement of flexibility when they end, right? So that's basically what this correlation coefficient is doing, is saying, are the measurements valid enough or are they reliable enough to assume that the same person was actually measured for each group, okay? So that's what this correction factor is that's inserted into the equation, okay? And whenever we look at this, you'll get a correlation coefficient section in the output. You just want to make sure that that R value is greater than, this should be greater than or equal to, okay? You want it greater than or equal to 0.8, indicating you have a strong positive relationship, okay? If R is less than 0.08, you reject the assumption, okay? So that would mean subjects' pre and post measurements are not similar enough to be considered to have come from the same set of subjects. In other words, we would have to say that we actually have independent samples instead of a paired sample, okay? Which, I mean, if based on your word as the researcher, you should know, right? And usually this comes out nicely. So it's just kind of a side note check type of thing, okay? But to add on, it needs to be a positive R and not a negative R, right? Because a positive R is going to help to, as this gets larger, right, values in the square root or the standard error are going to get smaller, right? And then basically that overall this is going to decrease the standard error of the difference, okay, based on how this formula is worked into the square root function, right? But with a decreased standard error, which has an inverse relationship to t, that would mean our t ratio increases. So when we compare paired samples to independent samples, it's actually easier to find significance in paired samples, okay? And I give you guys an example of that in the practice problems for this section. But for our null hypotheses for the main effect, again, they're exactly the same as an independent t-test. The only difference is that you have the same people in both the control group and the experimental group, okay? So for our volleyball example, we've got, right, again, the 12-week training program looking at ankle sprain injury rates. Instead of having two separate samples, maybe we only have 20 players and we take a measurement prior to the training program as well as a measurement post-training program, okay? So this is where whenever I give you guys research scenarios, looking into how the subjects are measured is really, really important, okay? But again, we have our dependent variable and we create our hypotheses saying, are the pre-test means of ankle sprain injuries going to be the same as the post-test means? Null hypothesis says there would be no significant difference or that the means would be equal. A research hypothesis says that they are going to be different in some way. Okay, so for your practice problems for the t-test, I only give you this one sample or one example where you have two sample information, right? And then I give you this opportunity. You're going to calculate if you would have significance for a paired t-test, and then use this information as if you had an independent t-test and see how those outcomes differ, which is going to highlight the concept where I was saying a paired test is easier to prove as significant compared to an independent t-test. Okay. Any general questions on paired samples t-tests?
Yeah, we're back on slide, where was it? You're slow, sorry. For the R values, you said it was greater than 0.08, correct?
0.8, 0.8. Mm-hmm.
So is it 0.08 for the less than?
Oh, good point. No, this should be 0.8, both 0.8.
Okay.
That's a good catch. Thank you. That was probably a result of me typing too fast. Okay, so 0.8. So you need a strong positive relationship. Anything less than a strong positive relationship is not good. Okay. Any other questions on paired t-tests?
So they're basically like algebra, like you said earlier. It's a plus b whole square and a square plus b, a square plus b square kind of formulas.
What are you referring to?
Like a standard error kind of
Oh,
thing?
this part?
Yeah, this part.
Yeah, kind of.
Okay.
Wait, so could you repeat again why the R is important in the paired samples?
Yeah, so we have to make sure that individuals, we know the same people are going to be measured twice, right, based on our independent variable groups. We just have to make sure that the relationship between their pre and post test values makes sense, right? So like I was saying, if we used a flexibility program and we're seeing like, or our stretching program, and how does that affect flexibility, right? Somebody who is not that flexible is not necessarily going to be expected to have really, really decreased or super low flexibility after the stretching program, but they also wouldn't be expected to have a super high increase in flexibility either. So what we're trying to say is that based on the effects of the flexibility or the stretch training or the stretching program, we should have relatively uniform results across our sample if the same people were measured, right? Because remember, this basically just means if you take two different variables, if we're doing pre-test and post-test on X and Y axes, it basically says when we line up those pairs of data, they're going to be tightly enclosed around a trend line or a line of best fit. Okay. Does that help make sense?
Yeah.
Okay, cool. All right, so we have a little bit left. One, we're going to look at the magnitude of difference. So if we're looking at the difference between the means, how, like, we might get a difference of 5, which isn't significant, but in a different unit of measurement, a difference of 0.5 would be significant, right? So we kind of have to look at what is, if we have significant results, is the actual magnitude of that difference, does it mean anything? Okay. So in other words, we can say what percentage of the observed difference is actually due to the treatment. And this again is different than the p-value, because the p-value is saying, is the difference significant or not? The magnitude of the difference is literally the difference between sample 1 and sample 2. Okay, we have a specific equation that we use. So for omega squared, this will come in when we look at ANOVAs. So we're kind of going to skip over that for now. But what you guys are going to be responsible for calculating is the effect size. Okay, we can also look at change and improvement. Again, we don't really touch on this in this class, so we'll skip over that as well. Right, but effect size is going to indicate how large our difference actually is. So we calculate it by taking the mean difference divided by the standard deviation of the control group. If you do not have a control group, then we use a pooled standard deviation, which is just the standard deviation of both samples put together. And I do an example of that in the activity, so it should make sense once you go through that process. But basically, we'll get values anywhere between 0 and 1. And the way that you kind of evaluate these effect sizes is very similar to evaluation of correlation coefficient strength. Right? So remember, correlation coefficients, we said anything between 0.1 and 0.3 is generally weak. 0.3 to 0.7 is moderate, 0.7 to 1 is strong. Those are kind of the same parameters we use for effect size, looking at how big the difference is. So if you have an effect size of 0.2, that tells you the difference is generally going to be small in terms of the units that you used. Same thing if your effect size is around 0.5, that indicates a moderate difference. 0.8 and above indicates a large difference. However, it is important to note the true meaning of your effect size is best judged in the context of the research question. So based on previous literature, if other people showed, let's say you're replicating a study design with a different sample of people, right? And the previous study had an effect size of 0.5, and you get an effect size of 0.5, right? Maybe that validates your effect size and saying like, well, this is the difference that we would have expected because we were able to replicate results from a previous study, right? But it's the difference, or how big the difference is, how significant that is. Again, significance is going to be based off the p-value, but as far as what that difference means to you as the researcher is based on the units of measurement that you're using, right? Because sometimes the effects of a treatment might have small differences or small effects on post-treatment outcomes, but they're actually quite significant as far as their effects on the person, okay? So just to keep that in mind, effect size just basically needs to be taken with a grain of salt, okay? And then the last thing, or the last equation you guys are responsible for this week, is the equation that we use to determine sample size. So I like to use a graphical representation with this, but sample size, remember, is directly related to power. So if you remember our truth sounding table where we looked at when the null hypothesis is true versus false, versus when you accept the null and reject the null, right? Kind of, we use that table. There's 4 different outcomes, 2 of which we would get type 1 or type 2 error, right? So remember, power was like the lower right corner or right box of the table that we created, saying that the test, it's a measurement of the test's ability to detect a real effect in the population. So it's when we reject the null and the null is actually false. So we have a true decision that we've made, right? And power is going to be 1 minus type 2 error. So, which is the probability of rejecting the null, or accepting the null when the null is false, right? It would be the opposite of power. So this is going to be dependent on 4 different factors. One is the alpha level set by the researcher. So you choose a level of confidence. That level of confidence is associated with a certain alpha value, right? It's also dependent on what that difference is between the 2 means that you've measured. It's going to be dependent on the variability within each of those groups, which we can relate back to z-scores, and it's going to be related to sample size. Sample size is going to be the most feasibly controlled variable, right? Because alpha, once that's set, it's kind of constant, right? The difference between the 2 means you can't control how your sample values come out. It's like whatever's measured is what you run with, assuming that they're normally distributed, right? And then standard deviation is kind of going to go along with your sample measurements as well as how big your sample size is. So sample size is going to be the most effective change that we can implement to increase power as much as we can. Okay, so this is my graphical representation. Okay, in this example, we're saying that x1 or sample 1, mean 1 is going to be our control group versus sample 2 is going to be our experimental group. Okay, so our control group is our basis of comparison, right? It's in a perfect world, perfectly representative of the normal population, right? And we're saying, does a treatment or does the whatever the manipulation is to the independent variable, or to this experimental group, does that actually have an impact or an effect, right? So in our distribution, or comparing our means, we have our sample 1 or our control group distribution. We're assuming that it's normal in this case. Okay, but within that distribution, for a two-tailed t-test, we have two alpha levels, one at the kind of high side of the distribution as well as one at the low side, right? Last week or 2 weeks ago, we identified that the area within the level of confidence is where we would accept our null hypothesis, and areas outside or in our region of rejection is where we would reject the null hypothesis and therefore accept the research hypothesis. Okay. So we take this control group sample mean and we compare it, right, to how far away it would be from this alpha. So remember, alpha is directly related to your level of confidence, right? Or you think Z always represents the area to the left of a given curve area. So if we're using a 95% level of confidence, that's associated with a total alpha of 0.05, right? In each of these tails, it would be 0.025. So the Z-score associated with a 95% level of confidence for a two-tailed test is 1.96. Right? That was given in your notes, so you can always refer back to those values. But there is a certain Z-score associated with the distance from this sample mean to where the area or region of rejection would exist. Okay. We then compare that sample mean or our control group mean to our experimental mean. And let's say our experimental group lands in this area compared to our control group distribution. Okay, so what we end up saying is that this overlapping area between these two distributions is where beta would exist, okay, or our type 2 error, because this would say if we chose to accept the null hypothesis, when the null hypothesis is actually false, right? Our sample compared mean landed in the region of rejection for this control group, right? But B, the overlapping area would be that we would accept the null when the null is false. So this is a type 2 error, okay? That type 2 error is going to have a Z-score as well, right? Where it's representing how far this second sample mean is from the original area of rejection, right? Or kind of the starting point for the area of rejection. So this is, again, Z, right, is the area to the left of the curve. So this would represent the probability of a type 2 error. Okay. From here, we know that power is 1 minus beta. So this whole orange area represents where our power is. And our goal in research is to make this area as large as possible. Usually we say 80% is a good cutoff, right, where you would accept about a 20% rate of type 2 error, okay? So 80% is what you're looking for in this area, okay? So with that being said, right, the difference between the means, x1 minus x2, is generally what we use to find our t, right, obviously divided by the standard error, but it's also comparable to the difference between these two means could also be said that it's z alpha plus z beta, right, or the difference from mean 1 to the area of rejection and the difference from mean 2 to the area of rejection, or the distance, right? So both of these together, we can basically find what Z beta should be, because we already know what Z alpha is based off of our alpha level that we set, right? Z beta is less commonly known. So to find that, all we need is the mean difference, or T, right, minus the alpha that we've chosen to work with, okay? Hooah! All right. So that's a very complex graphical representation. But when you actually do the sample size calculations, hopefully the integration of that graph makes sense with your processes. So generally, again, power is going to be 1 minus beta. Okay. Again, we use the comparisons of the means to find what z beta actually is, right? And this is, again, the z-score that represents the probability the researcher will make a type 2 error, right? Because it's the area to the left of the curve. So we want to usually keep this at about 20%, where we have a power of 80%, right? Z alpha, remember, is going to be representative of the probability that will make a type 2 or a type 1 error, okay? In the sense that we're going, it's the odds that we would reject the null when the null is true, okay? So with this information, right, evaluate where z beta is compared to the experimental mean, right, to decide if you should look up the positive or negative z-score. So z beta could be on, if we go back to this graph, right, in this case, it's on the lower end. If we had this sample mean on this side of the control group distribution, we would have a positive z-score for z beta, okay? Generally, what I like to do is just keep everything positive, where we're taking absolute differences. And I do explain that in the activity video when you're looking up sample sizes or when you're calculating sample sizes. So this is the actual equation that you guys have to know for the exam, okay? And it's derived from this basic formula that we just went over in the graphical representation, okay? It is going to assume that sample sizes are going to be the same and that standard deviations are going to be the same. So when you use standard deviation, usually you assume that the standard deviation is going to be of the control group. If not, similar to effect size, you use the pooled standard deviation, which is all of the data, okay? But pretty much you should be given standard deviation. You should know what the z-score for alpha is based on the level of confidence you set. And you should know, here's my cursor, you should know what the means of your samples are. So basically the only thing to figure out is the z-score for beta. And we can use the z-score table and the probability of 80% to figure out what the z should be. Okay, the same strategy that you use to find this z-score could be said to be the same if you're looking for an 85% level of power, if you're looking for a 75% level of power, right? So I do go through how to find that, but just keep in mind 80 is kind of our sweet spot, but other examples that I have or give to you guys might be different values. So it is important that you know how to use the Z table based on the power level that's given to you. Okay. All right, so the last thing we're gonna cover, and then I'll take questions, is to kind of pull all of this information together. So between our statistical inference lecture, the correlations and regression lecture, as well as our t-test lecture, basically when we infer sample information on a population, we take what the sample measurement is, or in this case, the difference of the sample measurements, right, for t-test this week, and we divide it by a standard error measurement, right? And then this is telling us how different our sample is from the population, right? So when we looked at z-scores and we wanted to see, right, how far a sample mean was from a population mean, right? We looked at distribution shape and divided by standard error to see how our sample skewness would compare, or sample kurtosis, right, would compare to a normally distributed population. When we looked at regressions, we calculated a t-statistic for a b coefficient to see how does this sample relationship that we've established in these equations, how does that relate back to what the true relationship or predictive relationship would be in a population, right? So we're dividing by standard error in regressions as well. And same thing in t-tests, again, inferring sample information to a population, we have to divide by standard error, either in the case of looking at the difference between a sample mean and an estimated population mean, or we're looking at, right, the difference between two means and where that actual difference would exist in a population. Okay, so everything is connected, and hopefully dots are starting to connect. Or if they're not connected now, they'll connect later this week as you kind of come back through this information. Okay, so that's pretty much it for today.